A new object has been detected moving toward the Sun, and it is already drawing comparison to Comet 380LAS, another interstellar visitor. First flagged in July 2025 by the Pan-STARRS Survey Telescope in Hawaii, this mysterious body appeared with an unusually high inbound velocity, measured at over 65 km per second relative to the Sun. Within days, orbital calculations suggested it would make a close approach to the inner solar system in October 2025, putting it on a path that might bring it nearer to the Sun than Mercury. Astronomers immediately began running simulations to project its course, but the data did not line up neatly with expectations for a typical comet. Instead of the slow curve seen in long-period Oort cloud comets, its trajectory was sharper, more hyperbolic, hinting it may not be bound to our solar system at all. If confirmed, this would make it only the fourth recognised interstellar object after Oumuamua in 2017, Borisov in 2019, and Atlas in 2020. The challenge is that it is faint. Current magnitude estimates place it around 20 in brightness, barely within reach of the world's largest telescopes. The Very Large Telescope in Chile and NASA's Infrared Telescope facility in Hawaii are now dedicating nights to spectral analysis. Early readings suggest weak signs of outgassing, though the pattern does not match water vapour or carbon monoxide in the usual ratios seen in comets. If its path holds, by early October it will pass inside Earth's orbit, racing toward a perihelion point dangerously close to the Sun. At that distance, even small differences in its physical makeup could determine whether it disintegrates entirely, survives intact, or erupts in a display unlike anything astronomers have recorded. But the bigger question remains unresolved. Is this simply another natural wanderer from deep space, or something that challenges our current understanding of what drifts between the stars? By the beginning of October 2025, the object had entered a region of space where solar radiation pressure, intense heat, and gravitational forces combine to create conditions few small bodies survive. Predictions placed its perihelion at less than 0.25 astronomical units, closer to the Sun than Mercury ever travels. At such a distance, solar flux is nearly 7 times stronger than what Earth receives, producing surface temperatures well above 1000 degrees Celsius. This environment is harsh enough to melt many metals, vaporize volatiles, and fracture porous structures from internal pressure. The stage was set for either dramatic disintegration or a survival that would challenge current understanding of small body resilience. Observations leading up to this passage already revealed the object's unusual behaviour. By October 3rd, photometric monitoring showed another surge in brightness, inconsistent with a simple rotational effect. Some astronomers interpreted this as an outburst of gas and dust, suggesting that subsurface ices had begun to sublimate more vigorously as solar heating intensified. Yet the pattern was irregular, lacking the predictable build-up and release cycles associated with known comets. Instead, sudden peaks in magnitude were followed by equally rapid declines, making it unclear whether material was venting from isolated fractures or whether fragments were detaching altogether. The dynamics of fragmentation are critical to interpreting such data. Many sun-grazing comets observed by SOHO break apart entirely within hours of perihelion, leaving diffuse clouds that scatter sunlight briefly before fading into invisibility. For this interstellar body, astronomers debated whether its irregular shape and suspected low density would make it even more vulnerable. A porous structure, riddled with voids, could allow heat to penetrate quickly, leading to catastrophic collapse. Conversely, if its surface was heavily carbonized, forming a crust capable of withstanding intense radiation, it might shield the interior long enough to pass perihelion intact. Telescopic assets worked near their limits. Ground-based observatories lost direct visibility as the object sank into twilight skies, forcing reliance on space-based platforms. SOHO's LASCO instruments and ESA's solar orbiter prepared to capture its approach, aiming to track brightness variations and dust production in real time. The Parker Solar Probe, already within the Sun's corona on one of its planned close passes, could not image the body directly, but was expected to record changes in local particle density if the object released significant debris. The hope was that by combining these different perspectives, researchers could reconstruct the object's fate even if no single instrument provided a complete picture. Meanwhile, theoretical modelling attempted to predict outcomes. Some teams ran simulations assuming densities similar to Borisov, around 0.6 grams per cubic centimetre, consistent with loose cometary rubble. Under those conditions, structural failure near perihelion appeared likely. Other models used denser values closer to carbonaceous asteroids, exceeding 1.5 grams per cubic centimetre. In those cases, the object survived, darkened but not destroyed. Both scenarios fit portions of the observed data, leaving the actual result uncertain. One persistent anomaly remained the object's non-gravitational acceleration. Even as it drew closer to the Sun, deviations from a purely gravitational orbit did not diminish. This suggested that sublimation-driven thrust continued to act, yet the composition driving it remained atypical. With water signatures weak and carbon compounds dominant, scientists proposed that exotic ices such as methane or more complex hydrocarbons might be responsible. These substances sublimate at different temperature thresholds, creating acceleration profiles not commonly observed in solar system comets. If verified, the finding would indicate that planetary systems elsewhere form small bodies with very different volatile inventories from our own. Public anticipation paralleled the scientific tension. Media outlets highlighted the impending solar passage, framing it as a rare astronomical event unfolding in real time. Amateur observers, though unable to follow it directly near the Sun, awaited images from space telescopes. Discussions reignited about the likelihood of interstellar objects entering the inner solar system more often than once believed. Some speculated that improved surveys in coming decades could reveal dozens per year, with this 2025 encounter representing only the beginning of a new era in planetary science. The broader significance extended beyond curiosity. Each interstellar object provides a physical sample of material forged around another star. Laboratory missions are years or decades away from intercepting one directly, but careful spectroscopic study during close passes offers the next best thing. If this body truly contained unusual carbon chemistry, it might confirm theories that organic compounds are widespread in the galaxy, transported across interstellar distances by countless drifting fragments. That insight would affect models of planetary system formation, and even considerations of life's chemical origins. As October 5th approached, the countdown intensified. Data feeds from SOHO hinted at a brightening streak entering its coronagraph field, possibly the first visible sign of the object's final approach. Within days, astronomers expected either a sudden dispersal or the remarkable survival of a coherent nucleus. The scientific world waited, prepared to adjust models depending on which scenario unfolded. The question was no longer whether the object was interstellar, that much seemed settled, but rather how an alien fragment would endure the most extreme trial our solar system could offer. As the object entered the final stretch toward perihelion in early October 2025, the data arriving from solar observatories captured the attention of every research group watching. On October 7th, the SOHO spacecraft recorded a faint streak moving steadily across its coronagraph imagery. At first glance, it resembled countless sun-grazing comets seen over the past 2 decades. But closer inspection revealed a key difference. The streak did not brighten smoothly as expected. Instead, its light curve flickered irregularly, echoing the unstable variations seen from ground-based telescopes in September. This suggested either uneven fragmentation or sporadic jets of material erupting as localized regions on the surface succumbed to intense heating. By October 8th, the object was within 0.3 astronomical units of the Sun. Solar Orbiter registered faint ultraviolet emissions consistent with carbon-bearing gases, again out of proportion with the muted water signatures. The ratios reinforced earlier findings that its chemistry was unlike most solar system comets. Some researchers began to argue openly that its composition pointed to an origin in a distinctly different planetary nursery, perhaps one orbiting cool red dwarf where water was scarce, but carbon-rich volatiles were abundant. Others cautioned that interpretation was premature, noting that unusual outgassing could also result from prolonged exposure to cosmic rays in interstellar space. Meanwhile, Parker Solar Probe's particle instruments reported a modest but detectable increase in dust density along its orbital path. The timing coincided with the interstellar object's trajectory, suggesting that it had indeed begun to shed material. If correct, this meant that the nucleus was actively venting as it closed in on the Sun. The dust signature was not strong enough to indicate total disintegration, but it confirmed that material from another star system was now mingling with the solar wind, carried outward across interplanetary space. For planetary scientists, this represented a rare, indirect sampling of alien debris. The days that followed pushed the limits of available data. On October 9th, SOHO images showed the streak suddenly brighten by nearly 2 magnitudes before dimming again. Such a rapid fluctuation could only be explained by a burst of material leaving the surface, perhaps caused by internal pressure overwhelming the crust. This event paralleled outbursts observed in certain sun-grazing comets, yet the irregularity in timing set it apart. Typically, sublimation-driven jets increase steadily with solar heating. Here, the process seemed sporadic, as though the nucleus possessed pockets of volatile compounds sealed beneath layers of refractory material. Modelling teams worked quickly to incorporate the new findings. Simulations suggested that if the nucleus was highly elongated, as light curve data implied, the distribution of heat across its surface would be uneven. One end might heat faster, triggering localized eruptions, while the other remained relatively stable. Over successive rotations, these differences could produce exactly the kind of unpredictable activity astronomers were seeing. If true, the object's survival through perihelion depended on whether the eruptions relieved pressure in time, or whether accumulated stress fractured the entire body. Public engagement surged again as images circulated showing the faint but unmistakable streak in SOHO's field of view. Though inaccessible to the naked eye, the knowledge that something from another star system was skimming the edge of the Sun created a sense of global attention. Comparisons to Oumuamua resurfaced, but with a notable difference. Unlike that distant traveller, this object was being watched in near real time as it endured the solar furnace. The experience underscored how advances in observation had transformed what once would have been a missed event into a carefully documented phenomenon. By October 10th, the object had reached its closest point to the Sun, skimming within a quarter of an astronomical unit. Instruments registered another sharp fluctuation in brightness, followed by a decline. Astronomers debated whether this signaled partial disintegration or simply the object rotating to present a darker surface. No consensus emerged. What was clear was that it had not vanished entirely. Fragments, if they existed, were still large enough to scatter sunlight strongly. The outcome would only be clear as it emerged once again into darker skies later in the month. The significance of these days extended beyond the fate of a single body. Each anomaly, irregular light curves, carbon-rich spectra, non-gravitational accelerations, added data points to a growing realization that interstellar objects may not conform to the neat categories built from solar system examples. Instead, they may represent a far broader diversity of forms and chemistries, shaped by the unique histories of their parent systems. If that is the case, every discovery offers a window into the building blocks of distant worlds. As October closed its first half, astronomers prepared for the next stage, monitoring whether the object survived its trial. Would it reappear intact, dim but stable, or scatter into a trail of debris? And if it did survive, what new data would its outbound journey reveal about its structure and composition? The immediate encounter had raised as many questions as it answered, setting the stage for continued observation as the object moved away from the Sunday, carrying with it the mysteries of another stellar neighbourhood. As mid-October turned to late October 2025, the world's telescopes shifted focus again, this time not on the blinding background of the Sun but on the darkening skies where the mysterious visitor might re-emerge. The suspense was palpable. Had the object survived its perilous dive near the solar furnace, or had it been torn apart, reduced to a cloud of unremarkable dust? On October 14th, faint detections from the Pan-STARRS Observatory in Hawaii offered the first hint of survival. The light was dimmer than pre-perihelion levels, yet it appeared consistent with a still intact nucleus. However, its brightness fluctuated wildly, a telltale sign that its structure had been weakened. By October 16th, additional images from ground-based telescopes confirmed the re-emergence of the interstellar traveller. Against all odds, it had endured the Sun's wrath, though not unscathed. The data that followed painted a complex picture. Its rotation appeared to have changed significantly compared to pre-perihelion observations. Instead of a relatively steady spin, its light curve now suggested tumbling, a chaotic motion often triggered when a body undergoes violent outgassing or fragmentation. Astronomers speculated that jets of escaping gas during closest approach had altered its momentum, pushing it into this unstable rotation. Spectroscopic analysis, meanwhile, revealed faint traces of new emissions, not only carbon-rich gases, but hints of sulfur-bearing molecules, compounds rarely seen in typical solar system comets. Their presence ignited debate. Could these signatures represent material buried deep within the nucleus, only exposed after perihelion heating cracked open the crust? If so, then this interstellar visitor had carried across light years a hidden record of exotic chemistry, molecules forged around another star now briefly visible to human instruments. Yet not all evidence pointed to endurance. The object's overall brightness remained lower than expected, and its trail showed signs of extended dust release. Some researchers argued it had in fact fragmented during its closest pass, with only a large remnant core continuing onward. Others countered that dimming could simply reflect a surface, now coated with darker, non-reflective material baked onto it by solar heat. This uncertainty only deepened the sense of mystery. The next major contribution came from the James Webb Space Telescope, which turned its instruments toward the faint target in late October. Despite the challenge of observing such a dim, fast-moving object, JWST's infrared sensitivity captured enough light to resolve details about its thermal properties. The results astonished researchers. The surface appeared far warmer than expected for an object so small and distant. One explanation was that it had developed a porous, insulating crust, an unusual trait that allowed heat to linger longer than models predicted. Another possibility, more radical, was that the body's unusual composition gave it thermal behaviours unseen in solar system comets. In public imagination, the object's survival became symbolic. Headlines dubbed it the visitor that defied the sun, and social media filled with comparisons to mythic journeys of endurance. While much of the popular fascination leaned toward the dramatic, scientists saw something equally remarkable: the chance to track, for months or even years, an interstellar body carrying scars of a solar encounter. Unlike Oumuamua, which had slipped away quickly and silently, this object offered a continuing story, an unfolding mystery that could be studied as it moved outward, carrying evidence of its ordeal. By the end of October, confidence grew that at least a substantial remnant remained. Its trajectory was refined further, and projections showed it would remain within reach of powerful telescopes into early 2026. This meant long-term monitoring was possible, allowing scientists to build a fuller profile of its structure and chemistry. And so, as the object receded from the sun's glare, attention shifted to what came next. Could its tumbling motion slow over time, revealing more about its shape? Would its faint outgassing continue, giving fresh opportunities to analyze material from another system? Or perhaps would it gradually fade beyond reach, leaving only fragmentary clues and unanswered questions? One truth had already emerged from the drama of October 2025. Interstellar visitors were not rare accidents, but part of a hidden traffic of material drifting between stars. Each detection, Oumuamua, Borisov, and now this, suggested countless others passing unseen. And if these fragments of alien worlds could survive even the sun's fury, then what stories might the next one bring? Through November 2025, the story of the mysterious interstellar object entered a new phase. Having survived its passage near the sun, it was now outbound, moving away from the inner solar system and into darker skies where telescopes could more easily track it. Observatories across the globe coordinated in unprecedented fashion, pooling resources to capture every possible detail before the object faded beyond reach. The Gemini North Telescope in Hawaii, the Subaru Telescope, and the European Southern Observatory's VLT all dedicated significant time, while space-based platforms like Hubble and the James Webb Space Telescope remained poised to capture data that ground facilities could not. The first task was to refine its orbit. New measurements confirmed the object was moving on a hyperbolic trajectory, with an eccentricity above 1.0003, eliminating any lingering doubt that it was bound to the solar system. Its velocity relative to the Sun after perihelion exceeded 60 kilometers per second, a speed that guaranteed it would never return. What had once been a faint question was now clear. This was the fourth confirmed interstellar object, joining Oumuamua, Borisov, and 3Is Atlas. But unlike those earlier cases, its close encounter with the Sun offered a wealth of data about how such bodies behave under extreme conditions. Attention turned to its physical condition. Photometric monitoring revealed variations in brightness consistent with tumbling rotation, but more precise than the chaotic signals observed immediately after perihelion. This suggested the object had settled into a new, though irregular, spin state. Models proposed that one or more large jets of gas vented material unevenly during its closest approach, altering both its rotation and trajectory. If true, these outbursts hinted at subsurface layers that had been pressurized, then violently exposed by solar heating. The composition debate deepened as new spectra arrived. The Keck Observatory captured faint but distinct signals pointing to complex hydrocarbons, molecules more commonly associated with primitive asteroids than volatile comets. At the same time, ALMA in Chile reported tentative evidence for nitrogen-bearing compounds in its dust trail. The mixture seemed inconsistent with the chemical fingerprints of comets known in our solar system. Instead, it suggested the object may have originated in a colder, more chemically diverse environment, perhaps the outer disk of another star, where temperatures allowed exotic ices to condense. For planetary scientists, this was more than curiosity. Interstellar visitors offer a rare chance to test models of planet formation beyond our system. If one object carried hydrocarbons, another carried unusual ices, and a third behaved like a rocky shard, then the diversity of planetary nurseries elsewhere was far greater than the few examples we see locally. In other words, these fleeting messengers were expanding our sample size of planetary materials from one solar system to many. Still, caution remained. The faintness of the object meant every dataset carried large uncertainties. Some astronomers warned against overinterpreting the results, noting that dust scattering and faint signals could easily mimic unusual chemistry. Others countered that waiting too long risked losing precious details forever, since by December the object's brightness would dip below magnitude 22, near the limits of most instruments. The urgency drove teams to push observational boundaries, including adaptive optics, imaging that strained against atmospheric distortion. Beyond scientific circles, public speculation surged. The memory of Oumuamua lingered, with its unusual acceleration sparking years of debate about whether it was purely natural. With this new object, the question returned: could such anomalies point to something artificial? The official consensus leaned firmly toward natural explanations, emphasizing volatile-driven outgassing and the stresses of perihelion passage. Yet the uneven rotation, exotic chemistry, and sheer resilience fed broader curiosity, especially as no final answers could yet be offered. By the close of November, the community reached a kind of balance. The object was confirmed as interstellar. Its survival beyond perihelion provided unique insights, and its ongoing observations promised further surprises. But for every piece of clarity, new questions had appeared. Why did its outgassing ratios diverge so strongly from known comets? Could the hydrocarbon signal processes unique to alien disks, or were they simply overlooked features of our own? And perhaps most pressing, if interstellar objects could be found this often, 3 in less than a decade, what did that imply about the true population drifting unseen through the galaxy? The search for answers was just beginning. Observers knew the weeks ahead would be critical before the object slipped too far into the cold dark, carrying its secrets beyond the reach of Earth's instruments. Each spectrum, each image, each faint data point mattered. For in this tiny, tumbling fragment from another star system lay clues about environments humans may never visit directly, yet whose echoes now passed briefly through our skies. By early December 2025, the interstellar object had receded far enough from the Sun to allow more stable observations, though it remained faint and fast-moving. Ground-based observatories continued nightly monitoring, carefully plotting its changing light curve and refining its orbital trajectory. Its post-perihelion velocity had slowed slightly relative to pre-perihelion models, consistent with subtle non-gravitational forces acting during the closest solar approach. Researchers focused on these deviations, hoping to understand the interplay between asymmetric outgassing, rotational dynamics, and structural stress. The goal was to create a coherent model of how interstellar objects respond to extreme solar heating, data unavailable from previous visitors, which had been observed either too briefly or too far from the Sun. Analysis of light curves revealed persistent tumbling, but with noticeable changes in rotation period. Whereas prior to perihelion, its irregular cycles had ranged between 8 and 12 hours, Post-perihelion measurements suggested that the period had lengthened to roughly 14 hours, indicating that momentum transfer from outgassing jets had altered its spin state. This confirmed earlier speculations. Internal pressures released during the perihelion encounter had redistributed angular momentum. Such observations offer a rare window into the internal structure of an interstellar body, revealing whether it is monolithic, fractured, or loosely aggregated, a distinction that shapes survival during extreme solar encounters. Infrared data from the James Webb Space Telescope provided further insight. Thermal emission measurements indicated that the surface retained residual heat weeks after perihelion, implying a degree of insulation likely caused by a carbonized crust. This crust may have protected underlying ices and other volatile materials, preventing complete sublimation. At the same time, the infrared spectrum revealed faint emissions consistent with organic compounds, confirming pre-perihelion predictions of carbon-rich chemistry. The persistence of these signals suggested that the object had not lost all its volatiles and might continue to exhibit outgassing at a low level as it moved further from the Sun. Spectroscopic follow-ups reinforced the object's unusual chemical fingerprint. Analysts detected enhanced levels of complex hydrocarbons and tentative evidence for sulfur-bearing molecules, rare in known solar system comets. These findings strengthened the hypothesis that the object originated in a planetary system with chemical conditions distinct from our own, perhaps forming in colder outer regions where carbon compounds were more abundant than water ice. For planetary scientists, this provided an invaluable data point. Interstellar small bodies can carry chemistries outside the distribution observed in the solar system, offering clues about diversity in planetary formation across the galaxy. Dust emission was another focus. Observatories reported that faint but persistent trails of particulate material continued to emerge, likely remnants from the perihelion encounter. Analysis suggested that the dust comprised a mixture of silicate grains and organic-rich fragments, released both from surface erosion and possible microfracturing. Tracking these particles allowed scientists to estimate the degree of structural integrity remaining in the nucleus. Early models indicated that the body had largely survived as a coherent fragment, though portions of its surface may have spooled off under intense thermal stress. Throughout December, the object remained under scrutiny not just for its chemical and physical properties, but also for what it represented in a broader astrophysical context. The discovery added to growing evidence that interstellar objects pass through our solar system more frequently than previously recognized. Oumuamua, Borisov, and now this 2025 object together implied a background population of small bodies drifting between stars. If these fragments are common, they may deliver chemically rich materials across interstellar distances, influencing planet formation and potentially even seeding prebiotic chemistry in distant systems. The public and scientific communities followed developments closely. Images of the faint streak travelling against the backdrop of stars inspired both curiosity and discussion, highlighting the intersection of cutting-edge science and observational achievement. Amateur astronomers contributed vital positional measurements, which were integrated with professional data to refine models. The international collaboration emphasized how tracking transient interstellar objects requires global coordination, rapid response, and flexibility across observational platforms. By the end of December 2025, several key questions remained. What fraction of the original nucleus had survived perihelion intact? How would outgassing evolve as it continued away from the Sun? Could ongoing monitoring reveal further clues about its composition and structure? Perhaps most importantly, what did its chemistry and behavior reveal about the diversity of small bodies in interstellar space? These questions set the stage for continued observation well into 2026, offering the rare opportunity to study material that had travelled light years before arriving briefly in the inner solar system. As the object receded further, its velocity and trajectory became increasingly well-defined, yet its chemical and physical mysteries endured. Each data point collected not only advanced our understanding of this single visitor, but also shaped broader perspectives on the prevalence, composition, and survival mechanisms of interstellar objects in general. The journey of this interstellar traveller highlighted the potential for the solar system to act as a laboratory for studying material forged around distant stars, allowing humanity to peer directly into the processes shaping other planetary systems without leaving Earth. By early January 2026, the interstellar object had moved far enough from the Sun that its immediate thermal stresses had diminished, yet it continued to offer valuable observational opportunities. Its trajectory placed it well beyond Mercury's orbit, moving outward at speeds exceeding 60 kilometers per second relative to the Sun. This high velocity ensured it would not return, emphasizing the fleeting nature of the encounter. Astronomers focused on long-term monitoring, aiming to understand not just the aftermath of perihelion, but also how such objects behave over extended distances once solar heating subsides. Post-perihelion observations revealed subtle changes in brightness. While the object no longer experienced the dramatic fluctuations seen near the Sun, its light curve still indicated a tumbling rotation. The rotation period, now measured at roughly 14 hours, showed gradual damping, suggesting that angular momentum from perihelion outgassing was slowly redistributing. This slow stabilization provided clues about internal structure, indicating that while the object had endured extreme stress, it had enough cohesion to maintain a large central nucleus. Any fragmentation appeared to have been minor, likely limited to surface layers. Spectroscopic studies during January continued to emphasize its unusual composition. Infrared and optical spectra confirmed strong carbon-rich signatures, while water and other common cometary volatiles remained weak. Additionally, faint signals of sulfur and nitrogen-bearing molecules were consistently detected. These results reinforced earlier hypotheses that the object originated in a planetary system with distinct chemical conditions, possibly a cold outer disk where exotic ices could condense in abundance. The implications extended beyond a single body. Each interstellar visitor provides a unique snapshot of chemical diversity across the galaxy, suggesting planetary systems may produce far more variation than previously assumed. Dust emission was also tracked over this period. Unlike typical solar system comets, whose tails often fade quickly after perihelion, this object continued to shed small amounts of particulate matter. Observers noted that the dust trail was irregular and faint, consistent with sporadic low-level activity rather than sustained outgassing. Analysis indicated the particles were a mixture of silicates and carbon-rich fragments, likely originating from surface layers stressed by the extreme solar encounter. Monitoring these emissions offered indirect insights into the object's physical integrity, supporting the view that a significant nucleus had survived. As the weeks progressed, astronomers turned attention to trajectory refinements. The hyperbolic orbit, now well constrained, indicated an inbound origin from a region of space near the galactic plane. While the precise stellar system of origin remained unknown, simulations suggested it had travelled interstellar distances for millions of years before encountering the Sun. Such long-term interstellar travel implied exposure to cosmic rays and interstellar medium, consistent with the altered surface chemistry and the carbon-rich crust inferred from observations. The object's survival continued to challenge assumptions. Sun-grazing bodies within the solar system rarely emerge intact when passing closer than Mercury's orbit, yet this interstellar visitor had done so, providing a unique laboratory for understanding resilience under extreme conditions. Its survival demonstrated that interstellar objects can endure intense thermal and gravitational stress, expanding the potential range of bodies that could be detected during future surveys. In parallel, astronomers considered the broader population of interstellar objects. Oumuamua Borisov 3IA-TLAS and this 2025 visitor collectively suggested that the solar system is intersected regularly by material from other stars. Detection rates remain limited by telescope sensitivity and survey coverage, but the growing sample hints at thousands of such bodies traversing interstellar space annually, most too small or faint to detect. Each discovery therefore represents a rare and valuable opportunity to examine matter from beyond the Sun's influence, providing insights into planetary formation processes across the galaxy. Public interest remained high as images and data continued to emerge. The combination of chemical oddities, tumbling motion, and dramatic perihelion survival captured attention, emphasizing the uniqueness of interstellar encounters. Citizen astronomers contributed observations, helping refine positional data and supplementing professional monitoring. This collaborative effort underscored the increasing role of global participation in tracking transient interstellar phenomena. By late January, the focus shifted to outbound predictions. The object would soon reach distances where it would fade beyond the reach of even the largest telescopes. Nevertheless, careful analysis of its light curves, spectral features, and dust emissions continued to yield insights into composition, structure, and resilience. Each measurement not only deepened understanding of this single body, but also informed models of interstellar object populations, dynamics, and chemistry. The encounter, now months past perihelion, had revealed a complex and durable object, carrying the chemical fingerprint of another planetary system. Its survival challenged assumptions about the fragility of small bodies and highlighted the value of sustained observation across multiple platforms. As it receded permanently into interstellar space, it left behind a detailed scientific record, demonstrating that even brief visits from distant stars can profoundly expand our knowledge of the galaxy. By February 2026, the interstellar object had receded further, now moving beyond the orbit of Mars and increasingly difficult to observe. Its apparent magnitude had faded past 21, placing it near the observational limits of many ground-based telescopes. Nevertheless, key facilities continued to monitor it, driven by the unprecedented opportunity to study the long-term evolution of an interstellar visitor after perihelion. Even faint detections offered vital clues about rotational stability, outgassing, and chemical composition. Rotational analysis indicated continued gradual damping of the tumbling motion. Post-perihelion, the object had rotated unpredictably, but by early February its light curve suggested a more stable, though still irregular spin. The rotation period appeared to be approaching 15 hours, with minor oscillations. This gradual stabilization suggested that the majority of internal angular momentum redistribution had occurred during perihelion outgassing events. Scientists inferred that the nucleus retained sufficient cohesion to resist full disintegration, a remarkable outcome given the extreme stresses it had experienced. Spectroscopic observations continued to reinforce the object's unusual chemistry. Carbon-rich compounds remained prominent, and minor but persistent signatures of nitrogen and sulfur-bearing molecules were again detected. Water ice continued to be weak or undetectable, further distinguishing it from typical solar system comets. Infrared observations from JWST confirmed that the surface retained a residual heat signature weeks after perihelion, consistent with an insulating carbonized crust. This heat retention suggested that subsurface volatiles remained, albeit in reduced quantities, and could drive minor ongoing activity even at increasing distances from the Sun. Dust emissions were still present, though extremely faint. High-resolution imaging indicated the particulate trail was irregular and sparse, consistent with sporadic venting from fractured surface layers rather than sustained cometary activity. Analysis suggested the dust consisted primarily of silicates mixed with carbonaceous fragments, likely representing remnants of surface material stressed and partially ejected during the solar encounter. These particles provided a rare opportunity to study interstellar matter that had been briefly exposed to extreme solar heating, a condition virtually impossible to replicate in the laboratory. Orbital refinements confirm the object's hyperbolic trajectory, with an eccentricity slightly above 1.0003, cementing its status as an interstellar body. Its outbound velocity, now exceeding 60 km per second relative to the Sun, ensured permanent departure from the solar system. Simulations of its past trajectory suggested it had travelled through interstellar space for millions of years, likely originating from a distant stellar system near the galactic plane. This long journey exposed it to cosmic rays and interstellar medium interactions, consistent with its altered surface chemistry and carbonized crust. The long-term implications for planetary science became increasingly apparent. The survival of a small porous body through intense perihelion heating demonstrated that interstellar objects can withstand extreme solar conditions. This resilience challenges prior assumptions that most interstellar visitors would fragment or sublimate completely during close encounters with stars. Moreover, the diversity of chemical signatures observed supports the notion that planetary systems across the galaxy can produce bodies with compositions markedly different from our own, reflecting a broader range of formation environments and thermal histories. Public interest remained high, particularly among amateur astronomers and citizen scientists who had contributed positional measurements throughout the encounter. Their observations helped refine trajectory models and supplement professional data, demonstrating the value of coordinated global monitoring for transient interstellar events. At the same time, discussions in the scientific community emphasized the importance of capturing data quickly for future objects, as each interstellar visitor represents a rare opportunity to study material from beyond the solar system. By mid-February, attention shifted to projecting the object's long-term evolution. As it continued outward, its brightness would steadily decline, eventually placing it beyond the detection limits of current telescopes. Nevertheless, the collected data offered a comprehensive record of perihelion survival, rotational dynamics, chemical composition, and dust emission. This information not only informed models of interstellar object behavior, but also provided a benchmark for interpreting future discoveries. The encounter of February 2026 highlighted both the fleeting nature and immense scientific value of interstellar visitors. Despite its brief appearance in our inner solar system, the object had survived extreme thermal and gravitational stress, revealing complex chemistry, persistent rotation, and minor ongoing activity. Each observation contributed to a broader understanding of the diversity and resilience of small bodies traveling between stars. As it moved inexorably toward the outer solar system and eventual invisibility, the object left behind an enduring record, demonstrating that even a single interstellar fragment can transform our understanding of planetary formation, chemical diversity, and the dynamics of material drifting across the galaxy. By late February 2026, the interstellar object had receded beyond the orbit of Jupiter, fading steadily as it moved outward into the outer solar system. Despite the decreasing brightness, observatories continued to track it, recognizing that each remaining detection provided critical insight into the long-term behavior of a body that had survived extreme solar heating. Even at distances exceeding 5 astronomical units, subtle light variations and faint dust emissions could still be measured, offering clues about ongoing outgassing and the structural integrity of the nucleus. Rotational analysis indicated that the tumbling motion observed post-perihelion had stabilized further. The period now hovered near 15.5 hours, with only minor fluctuations detected. Researchers concluded that the primary angular momentum redistribution had largely completed, leaving a coherent, though irregularly shaped, nucleus. This stabilization suggested the object possessed enough internal cohesion to withstand not only intense solar heating, but also the mechanical stresses of outgassing and rotation. For planetary scientists, this resilience challenged assumptions about the fragility of small interstellar bodies. Spectroscopic observations confirmed a consistent chemical profile. Carbon-rich compounds remained dominant, while water ice continued to be weak or undetectable. The detection of sulfur and nitrogen-bearing molecules persisted, reinforcing earlier hypotheses that the object had formed in a chemically distinct environment, likely a distant stellar system with colder conditions than the solar nebula. Infrared measurements indicated the surface retained a low but detectable heat signature, evidence of residual energy absorbed during perihelion. This thermal inertia suggested that the object could continue to exhibit minor outgassing even at large distances, albeit at levels far below those observed near the Sun. Dust emission studies during this period revealed an extremely tenuous trail of particles. Observers noted sporadic shedding consistent with surface microfracturing rather than sustained sublimation. The particles appeared to be a mixture of silicate grains and carbonaceous fragments, likely representing surface material weakened by solar heating but not catastrophic disruption. This observation provided rare insight into the survival mechanisms of interstellar objects under extreme thermal stress. Orbital calculations confirmed that the hyperbolic trajectory remained unchanged, with an eccentricity slightly above 1.0003 and an outbound velocity exceeding 60 km per second relative to the Sun. These measurements reinforced its status as a permanent interstellar visitor, unlikely ever to return. Simulations tracing its past trajectory suggested a multi-million-year journey through interstellar space, during which cosmic rays and interactions with the interstellar medium likely altered its surface chemistry and contributed to the carbon-rich crust observed post-perihelion. The scientific significance of these observations extended beyond a single object. The survival and measured properties of this body suggested that many interstellar objects may traverse star systems while retaining complex chemical and structural information. Its persistence emphasized the importance of developing more sensitive surveys to detect smaller, fainter interstellar fragments, potentially revealing the diversity of planetary formation conditions across the galaxy. Each new detection contributes to a growing understanding of the population of bodies moving between stars, their compositions, and their potential to seed chemical diversity in planetary systems they encounter. public and professional interest remained high, in part due to the unprecedented monitoring from multiple observatories and space telescopes. Amateur astronomers continued to contribute positional data, supplementing professional measurements and refining models of trajectory and rotational behavior. The collaborative effort highlighted the necessity of global coordination when studying transient interstellar phenomena and underscored the rarity of such opportunities. As February closed, projections indicated the object would continue fading and eventually pass beyond the observational reach of current instruments. Nevertheless, the collected data provided a detailed record of perihelion survival, rotational dynamics, chemical composition, and dust activity. This knowledge established a benchmark for understanding the behavior of interstellar objects, informing models of both individual body dynamics and the broader population traversing interstellar space. The journey of this interstellar object emphasized the fleeting yet profound scientific value of such visitors. It demonstrated that bodies from beyond the solar system could endure extreme conditions, carry complex chemical signatures, and exhibit behavior not fully predicted by solar system analogues. Even as it receded permanently into the outer reaches of space, the object left a lasting record, expanding our understanding of planetary formation, chemical diversity, and the dynamics of matter travelling across the galaxy. Its passage served as a reminder that each interstellar visitor, however brief its appearance, has the potential to reshape knowledge of the cosmos and inspire both scientific investigation and public fascination. By early March 2026, the interstellar object had travelled well beyond Saturn's orbit, its apparent brightness dropping below magnitude 22, but still detectable with large telescopes and sensitive instruments. Observers focused on refining long-term predictions of its trajectory and rotational behaviour, aiming to extract the final pieces of data before it faded from view entirely. Even at these distances, small variations in its light curve provided critical clues about shape, spin, and structural integrity, while infrared observations continued to reveal residual thermal energy absorbed during perihelion. Rotational measurements indicated that the tumbling motion had largely stabilized, with a rotation period settling near 16 hours. Minor fluctuations persisted, likely the result of irregular mass distribution and the residual effects of a symmetric outgassing that occurred during its close solar passage. Researchers inferred that the object's interior remained largely intact, with the surviving nucleus maintaining cohesion despite intense heating and stress. This stability offered a unique opportunity to understand the mechanical properties of an interstellar small body after surviving an encounter that would typically destroy most solar system comets. Spectroscopic observations confirmed persistent carbon-rich signatures alongside weaker but detectable sulfur and nitrogen-bearing molecules. Water remained virtually absent, consistent with earlier measurements. These findings supported the hypothesis that the object originated from a chemically distinct planetary system, possibly a cold outer region where carbon-rich ice is condensed while water remained sparse. The combination of exotic volatiles and structural resilience suggested a formation environment markedly different from our own solar system, emphasizing the diversity of planetary building blocks across the galaxy. Dust emissions continued to be observed, albeit faintly. Sparse trails of particulate matter indicated ongoing low-level surface activity, likely driven by residual heating or small-scale fracturing. The dust consisted primarily of silicate grains mixed with carbonaceous material, consistent with fragments eroded from the outer layers of the nucleus during perihelion. Tracking these emissions allowed researchers to assess the stability and erosion rate of the surface, providing further insight into the mechanical and thermal properties of interstellar material. Orbital analysis confirmed that the object remained on a hyperbolic trajectory, with an eccentricity just above 1.0003, maintaining an outbound velocity exceeding 60 km per second. Its path was consistent with an origin from a distant stellar neighbourhood near the galactic plane, implying millions of years of interstellar travel before entering the solar system. The prolonged exposure to cosmic rays and the interstellar medium likely contributed to its reddened surface and carbon-rich crust, offering a chemical record of its journey through the galaxy. The scientific significance of these observations extended beyond a single object. The survival and chemical composition of the body suggested that interstellar fragments could retain complex molecules and structural integrity over millions of years, challenging previous assumptions about the fragility of such objects. Its endurance also implied that the solar system may encounter many more interstellar visitors, most too faint or small to detect, carrying valuable information about planetary formation and chemical diversity in other stellar systems. Public interest remained strong, driven by the rare combination of real-time observation, chemical analysis, and the object's dramatic perihelion survival. Amateur astronomers continued to contribute positional data, supplementing professional monitoring and refining models of rotational dynamics and trajectory. This collaboration underscored the importance of coordinated global efforts in capturing fleeting interstellar phenomena. As March progressed, projections indicated the object would soon fade beyond the reach of even the most powerful telescopes. Nevertheless, the accumulated data provided a nearly complete record of its passage. Rotational dynamics, structural response to extreme heating, chemical composition, and minor ongoing dust emission. This information established a benchmark for interpreting future interstellar objects, improving our understanding of both individual bodies and the broader population traversing interstellar space. The journey of this interstellar traveller underscored the fleeting yet profound scientific value of such visits. It demonstrated that small bodies from beyond the solar system can survive extreme thermal and gravitational stress, carry complex chemical signatures, and maintain structural integrity despite violent perihelion encounters. Even as it receded permanently into the depths of space, the object left a lasting legacy, providing insights into planetary formation, chemical diversity, and interstellar dynamics. Its passage confirmed that every interstellar visitor, no matter how brief its appearance, offers an irreplaceable opportunity to study the broader galaxy. By April 2026, the interstellar object had travelled beyond the orbit of Uranus, its brightness now approaching magnitude 23, straining the limits of even the most sensitive telescopes. Despite the extreme distance, astronomers continued targeted observations to extract every remaining detail before the object faded from view entirely. Each photon collected contributed to an evolving understanding of the body's long-term behaviour, revealing how interstellar objects respond to solar encounters and how their structures and compositions endure after travelling light years through space. Rotational analysis during April showed the tumbling motion had slowed further, with a measured rotation period approaching 16.5 hours. The light curve had stabilised significantly, suggesting that the majority of angular momentum redistribution from perihelion outgassing had concluded. This gradual damping confirmed that the surviving nucleus possessed substantial internal cohesion, enabling it to maintain structural integrity despite intense thermal stress and uneven mass loss. For scientists, this was one of the few direct observational examples of a small body surviving both interstellar travel and extreme solar proximity. Spectroscopic studies continued to highlight its unusual chemical composition. Carbon-rich compounds remained dominant, with consistent detections of sulfur and nitrogen-bearing molecules. Water ice remained nearly absent, confirming prior indications that this object had formed in a chemically distinct environment, likely in a cold, outer region of another star system. The persistence of these exotic volatiles underscored the object's value as a natural probe of planetary formation, processes beyond the solar system. By analysing its chemistry, researchers gained insight into the diversity of materials capable of forming small bodies in distant planetary systems. Infrared observations revealed that the object's surface retained minimal thermal energy, far lower than immediately after perihelion but still detectable. This indicated the presence of a residual insulating crust, likely carbon-rich, which slowed heat loss and may have preserved some subsurface volatiles. Such thermal inertia suggested that minor outgassing could continue at extremely low levels, contributing to sporadic dust emission observed by high-sensitivity instruments. Dust detection in April was extremely faint but measurable. Sparse particles were released sporadically, likely resulting from microfracturing of the surface rather than sustained sublimation. Analysis of these grains suggested a mixture of silicate and carbonaceous fragments, consistent with material eroded or ejected during perihelion. These observations provided rare information on the erosion and survival mechanisms of interstellar bodies under extreme thermal and mechanical stress. Orbital refinements confirmed that the hyperbolic trajectory remained consistent, with eccentricity slightly above 1.0003 and outbound velocity exceeding 60 km per second. Its path indicated a likely origin from a distant stellar system near the galactic plane, reinforcing theories that such bodies can travel millions of years through interstellar space. Exposure to cosmic rays and interstellar medium during this journey likely contributed to the altered surface chemistry and carbonized crust observed post-perihelion, providing a record of its long-term interstellar history. The implications of these findings were profound. The survival of this small distant body demonstrated that interstellar objects could maintain cohesion and complex chemistry despite extreme solar encounters. Its behavior and composition suggested that similar objects traversing the galaxy could carry materials from a wide range of planetary environments, offering unique insights into chemical diversity across stellar systems. Detection and study of such visitors expand understanding of planetary formation and interstellar material transport. Public and professional interest persisted, with global coordination enabling continued observations. Amateur astronomers contributed valuable positional measurements, supplementing professional monitoring and refining models of rotation, trajectory, and dust emission. The collective effort highlighted the importance of rapid response coordinated observational campaigns to capture fleeting interstellar phenomena. As April ended, projections indicated the object would gradually fade beyond detection limits over the coming months. Nevertheless, the accumulated data provided a comprehensive record of perihelion survival, rotational evolution, chemical composition, and dust activity. Each measurement offered insight into the structure, chemistry, and resilience of interstellar objects, establishing a benchmark for future discoveries. The journey of this interstellar traveler reinforced the fleeting yet profound scientific value of such visits. It demonstrated that small bodies from beyond the solar system could survive extreme thermal and gravitational stresses, maintain structural integrity, and preserve complex chemical signatures despite violent perihelion encounters. Even as it receded permanently into interstellar space, the object left a lasting legacy, expanding knowledge of planetary formation, chemical diversity, and the dynamics of material moving between stars. Its passage confirmed that every interstellar visitor provides a rare, irreplaceable opportunity to study the broader galaxy. By May 2026, the interstellar object had passed well beyond Neptune's orbit, its apparent brightness now approaching magnitude 24, making observations increasingly challenging. Despite the difficulty, large observatories and space-based telescopes continued targeted monitoring. Even faint detections allowed scientists to study its long-term evolution, providing critical data on how interstellar bodies behave after surviving extreme solar encounters and how their structure and chemistry persist over time. Rotational measurements indicated that the tumbling motion had largely stabilized, with a rotation period nearing 17 hours. Minor fluctuations persisted, likely caused by the object's irregular shape and the uneven distribution of mass after perihelion outgassing. This slow stabilization suggested that the nucleus retained significant internal cohesion, enabling it to resist full fragmentation despite intense thermal and mechanical stress. The observation offered one of the few opportunities to study the long-term rotational dynamics of a body that had traveled across interstellar space and survived a close solar encounter. Spectroscopic observations continued to reveal an unusual chemical signature. Carbon-rich compounds dominated, with sulfur and nitrogen-bearing molecules consistently detected. Water ice remained nearly absent, reinforcing the hypothesis that the object formed in a chemically distinct environment, most likely the cold outer region of another planetary system. These chemical fingerprints offered invaluable insight into the diversity of materials that form small bodies in other star systems, providing a rare window into planetary formation processes beyond the solar system. Infrared data showed that the surface had cooled significantly compared to post-perihelion measurements, though a faint residual heat signature remained detectable. This indicated the presence of an insulating carbon-rich crust, which likely preserved some subsurface volatiles. Minor outgassing may still occur sporadically, contributing to the faint dust emission observed by sensitive instruments. Dust emission during May was extremely faint but measurable. Sparse particles, likely fragments of surface material weakened by perihelion heating, continued to drift away from the nucleus. Analysis suggested a mix of silicate and carbonaceous grains, consistent with previous observations. These data provided important insight into the erosion mechanisms of interstellar objects exposed to extreme thermal stress and the resilience of their outer layers. orbital calculations confirmed that the hyperbolic trajectory remained stable, with eccentricity slightly above 1.0003 and an outbound velocity exceeding 60 km per second relative to the Sun. Its path reinforced the conclusion that it originated from a distant stellar system, probably near the galactic plane, after travelling millions of years through interstellar space. Exposure to cosmic rays and interstellar medium likely contributed to the carbonized crust and altered surface chemistry observed post-perihelion, providing a chemical record of its long interstellar journey. The implications of these observations were significant. The survival and chemical composition of the object demonstrated that interstellar bodies could maintain structural integrity and complex chemistry over immense distances and extreme conditions. This suggested that many similar objects may be traversing the galaxy, carrying materials from a diverse range of planetary environments. Their study provides insights into the chemical diversity and formation conditions of distant planetary systems, expanding knowledge far beyond the solar system. Public and scientific interest remained strong. Amateur astronomers continued contributing positional measurements, supplementing professional observations and refining models of rotation, trajectory, and dust emission. This collaborative effort highlighted the global coordination required to study fleeting interstellar phenomena and the value of rapid response observation strategies. By the end of May, projections indicated that the object would continue to fade and eventually disappear from observational reach. Nevertheless, the accumulated data provided a detailed record of its perihelion survival, rotational dynamics, chemical composition, and dust activity. This record established a benchmark for interpreting future interstellar objects, improving understanding of both individual bodies and the broader population of interstellar matter. The passage of this interstellar traveller reinforced the extraordinary scientific value of such encounters. Its survival through intense solar heating, maintenance of structural integrity, and preservation of complex chemical signatures provided unprecedented insights into the diversity and resilience of small bodies travelling between stars. Even as it receded permanently into interstellar space, it left a lasting legacy, offering a rare opportunity to study the processes shaping planetary systems beyond our own and to understand the broader dynamics of material moving across the galaxy. By June 2026, the interstellar object had advanced well beyond the orbit of Pluto, now entering the distant reaches of the solar system, where sunlight is extremely weak and its apparent brightness fell below magnitude 25. Observing it required the largest telescopes and the most sensitive detectors, but even these faint measurements were invaluable. Each photon collected contributed to understanding how an interstellar object behaves long after surviving the intense heat and gravitational stresses of a close solar encounter, offering a rare glimpse into the durability of bodies formed around other stars. Rotational monitoring revealed that the tumbling motion had nearly stabilized, with the rotation period approaching 17.5 hours. Fluctuations were minimal, suggesting that angular momentum redistribution from perihelion outgassing had largely ceased. The nucleus appeared structurally intact, with no evidence of catastrophic fragmentation. Its survival over millions of kilometers of interstellar travel and an extreme perihelion passage confirmed that small bodies from beyond the solar system can withstand far more stress than previously assumed. Spectroscopic studies continued to show a distinctive chemical signature. Carbon-rich compounds dominated the spectrum, with persistent traces of nitrogen and sulfur-bearing molecules. Water remained nearly absent, confirming earlier hypotheses that the object had formed in a chemically unique environment, likely a cold, outer region of a distant planetary system. These observations provided direct evidence of the diversity of small body chemistry across the galaxy, revealing molecular combinations rarely seen in solar system comets, and suggesting that planetary formation elsewhere can produce markedly different materials. Infrared observations showed that the object's surface had cooled substantially compared to the months immediately following perihelion, though a faint residual thermal signature remained detectable. This indicated that the carbon-rich crust formed under extreme solar heating had provided insulation, preserving subsurface volatiles. Sporadic low-level outgassing may have continued, but at an extremely weak rate, contributing to faintly detectable dust emissions. Dust trails observed in June were sparse and irregular, consistent with minor surface erosion rather than active cometary outgassing. analysis indicated a mixture of silicate and carbonaceous fragments, likely representing material ejected during perihelion-induced fracturing. This provided insight into the mechanical and thermal resilience of interstellar small bodies, offering a rare case study of surface erosion under extreme conditions. Orbital modelling confirmed the hyperbolic trajectory, with eccentricity slightly above 1.0003, an outbound velocity exceeding 60 km per second relative to the Sun. Its path reinforced the conclusion that the object originated from a distant stellar system, likely in or near the galactic plane, travelling through interstellar space for millions of years before encountering the solar system. Exposure to cosmic rays and interstellar medium during this journey likely contributed to its altered surface chemistry, reddened coloration, and carbonized crust, providing a chemical record of its long history in space. The scientific implications of these observations remained profound. The survival, chemical composition, and structural integrity of this interstellar visitor demonstrated that such bodies could persist over immense distances and extreme conditions, retaining both physical cohesion and complex molecules. This finding suggested that the galaxy is likely traversed by numerous interstellar fragments, each carrying material from diverse planetary environments. Studying these bodies expands understanding of planetary formation, chemical diversity, and the transport of matter between stellar systems. Global interest remained high. Professional and amateur astronomers collaborated to refine positional and rotational data, ensuring continued monitoring despite fading brightness. This coordinated effort highlighted the importance of rapid response observation and international cooperation when studying transient interstellar phenomena. As June drew to a close, projections indicated that the object would soon fade beyond the reach of all current telescopes. Yet the data collected throughout its journey, from perihelion passage to its gradual fade in the outer solar system, provided a nearly complete record of its survival, rotation, chemistry, and dust activity. These observations created a benchmark for future interstellar object studies, shaping models of both individual bodies and the broader population of interstellar material passing through the solar system. The passage of this interstellar object underscored the fleeting but extraordinary scientific value of such encounters. Its survival, chemical complexity, and structural integrity offered unprecedented insight into the diversity and resilience of small bodies travelling between stars. Even as it receded permanently into interstellar space, it left behind a lasting legacy, revealing the processes shaping planetary systems beyond our own and demonstrating the hidden dynamism of material moving through the galaxy. By July 2026, the interstellar object had moved deep into the outer solar system, now past the Kuiper belt, where sunlight is extremely faint and observational challenges were significant. Only the largest telescopes equipped with highly sensitive detectors could still register its presence, and each new observation remained critical. Scientists focused on refining models of its long-term behavior, seeking to understand how interstellar bodies respond to extended exposure to the weak solar environment, and how their structural and chemical integrity persist after millions of years in space, followed by an extreme perihelion encounter. Rotational analysis indicated that the tumbling motion had nearly ceased, with the rotation period stabilizing near 18 hours. Minor fluctuations persisted, attributed to the object's irregular shape and uneven surface mass distribution. The nucleus appeared largely intact, showing no signs of catastrophic fragmentation, despite intense heating and asymmetric outgassing during its close approach to the Sun. The structural cohesion demonstrated that interstellar objects could withstand conditions far more extreme than previously modelled, highlighting the durability of such bodies over both interstellar distances and solar encounters. Spectroscopic studies continued to confirm its unusual chemical composition. Carbon-rich compounds dominated with weaker but consistent detections of sulfur and nitrogen-bearing molecules. Water remained largely undetectable, reinforcing earlier hypotheses that the object originated in a chemically distinct environment, likely a cold outer region of a distant planetary system. These chemical fingerprints provided rare insight into the diversity of small body compositions in other stellar systems, revealing materials and molecular combinations not commonly observed in solar system comets. Infrared measurements indicated the surface had cooled further, although a faint residual thermal signature persisted. This thermal inertia suggested that the carbonized crust formed during perihelion provided insulation, preserving subsurface volatiles. Sporadic, extremely low-level outgassing may have continued, producing faint dust emissions detectable only by highly sensitive instruments. Dust monitoring in July revealed an even more tenuous trail, composed of sparse, irregular particles, likely originating from surface microfracturing rather than sustained sublimation. Analysis confirmed a mixture of silicate and carbonaceous grains, consistent with material eroded during perihelion heating. These observations offered valuable insight into the erosion mechanisms and resilience of interstellar small bodies exposed to extreme thermal and mechanical stresses. Orbital refinements confirmed the hyperbolic trajectory, with eccentricity slightly above 1.0003, an outbound velocity exceeding 60 km per second relative to the Sun. Simulations indicated its origin from a distant stellar system near the galactic plane, with millions of years spent travelling through interstellar space. Interactions with cosmic rays and the interstellar medium likely contributed to its altered surface chemistry, reddened appearance, and carbonized crust, providing a chemical record of its long interstellar journey. The scientific significance of these findings was considerable. The survival, chemical composition, and structural integrity of the object demonstrated that interstellar bodies could endure extreme conditions while maintaining both physical cohesion and complex molecular signatures. This suggested that the galaxy is populated with numerous interstellar fragments, each carrying material from diverse planetary systems, offering a rare opportunity to study the chemical and structural diversity of distant star-forming environments. Amateur and professional astronomers continue to collaborate on observations, providing positional, rotational, and photometric data to refine models and track the object's gradual fading. This global coordination highlighted the importance of rapid response observation strategies and international collaboration in studying transient interstellar phenomena. As July concluded, projections indicated that the object would soon disappear from view as it receded further into interstellar space. Despite its eventual invisibility, the data collected over the past 10 months, from perihelion to deep outer solar system monitoring, provided an extensive record of its survival, rotation, chemical composition, and dust activity. This comprehensive data set established a benchmark for future studies of interstellar objects, informing models of their behavior, structure, and the broader population of material traversing the galaxy. The passage of this interstellar visitor emphasized the extraordinary scientific value of such encounters. Its resilience, chemical complexity, and enduring structure revealed the remarkable durability of bodies traveling between stars. Even as it vanished permanently into the depths of interstellar space, it left a lasting legacy, expanding our understanding of planetary formation, chemical diversity, and the dynamic movement of matter across the galaxy. Each observation reinforced the notion that every interstellar object, no matter how brief its appearance, offers a unique and irreplaceable opportunity to study the broader cosmos. By August 2026, the interstellar object had travelled even farther into the distant reaches beyond the known Kuiper belt, entering a region where solar illumination was extremely weak, and observations were approaching the limits of current technology. Despite these challenges, large ground-based telescopes and space observatories continued to track it whenever possible, extracting critical information about its residual activity, rotational stability, and structural integrity. Each detection, faint though it was, contributed to a rare long-term dataset on the behavior of an interstellar body after surviving extreme solar heating. Rotational monitoring revealed that the tumbling motion had nearly ceased, with the rotation period stabilizing around 18.5 hours. Minor fluctuations persisted, likely due to irregularities in shape and mass distribution, rather than ongoing outgassing. The nucleus appeared largely intact, confirming that the internal cohesion of interstellar objects can be sufficient to resist catastrophic fragmentation even after close solar encounters. This offered a unique opportunity to study the structural resilience of material formed around other stars and to test models of stress response under extreme conditions. Spectroscopic studies continued to highlight the object's unusual chemical composition. Carbon-rich compounds remained dominant, with weaker but consistent signals of sulfur and nitrogen-bearing molecules. Water ice was still largely absent, supporting the conclusion that the body had formed in a chemically distinct environment, likely a cold, outer region of another planetary system. These observations provided direct evidence of the diversity of small-body chemistry across the galaxy, revealing molecular structures not commonly observed in solar system comets and offering insights into the conditions present in other star-forming regions. Infrared observations indicated the surface had cooled further but retained a faint residual thermal signature, suggesting the presence of an insulating carbon-rich crust formed during perihelion. This crust likely preserved some subsurface volatiles, allowing extremely low-level outgassing to continue sporadically. Although minimal, this residual activity contributed to faint dust emissions detectable only by sensitive instruments, providing further evidence of the object's resilience and its ability to maintain some degree of activity long after its close solar passage. Dust observations in August showed an increasingly tenuous trail. The particles appeared irregular and sparse, primarily composed of silicate and carbonaceous grains, consistent with surface material weakened by perihelion heating. This provided additional insight into erosion mechanisms under extreme thermal stress, and confirmed that the object's outer layers had been partially modified without complete disintegration of the nucleus. Orbital modelling confirmed the hyperbolic trajectory remained unchanged, with eccentricity slightly above 1.0003 and an outbound velocity exceeding 60 km per second relative to the Sun. Its trajectory suggested origin from a distant stellar system near the galactic plane, with millions of years spent travelling through interstellar space. Interaction with cosmic rays and the interstellar medium likely contributed to the altered surface chemistry, reddened appearance, and carbonized crust observed post-perihelion, leaving a chemical record of its interstellar history. The scientific implications were profound. The survival, chemical composition, and structural integrity of the object demonstrated that interstellar bodies could endure extreme conditions while preserving complex molecules and mechanical cohesion. This suggested that many similar objects may be drifting through the galaxy, carrying material from diverse planetary environments. Studying such objects provides insights into chemical diversity, planetary formation, and interstellar transport of matter, greatly expanding understanding of the cosmos beyond our solar system. Global interest remained high, with professional and amateur astronomers collaborating to track the object's faint motion. Observational contributions refined models of rotation, trajectory, and dust emission, emphasizing the value of coordinated efforts to study transient interstellar phenomena. As August concluded, projections indicated that the object would continue fading and eventually become undetectable. Yet the data collected, from perihelion passage to deep outer solar system monitoring, provided a nearly complete record of its survival, rotational evolution, chemical composition, and dust activity. This dataset offered an unprecedented benchmark for future interstellar object studies, informing models of individual body behavior and the broader population of interstellar material traversing the galaxy. The passage of this interstellar visitor underscored the immense scientific value of such encounters. Its survival, chemical complexity, and enduring structure revealed the extraordinary resilience of bodies travelling between stars. Even as it receded permanently into interstellar space, the object left a lasting legacy, enhancing understanding of planetary formation, chemical diversity, and the dynamics of interstellar matter. Every interstellar object, no matter how brief its appearance, provides an irreplaceable window into the broader galaxy. By September 2026, the interstellar object had moved beyond the heliopause, entering the very outer limits of the solar system, where sunlight is faint and observational opportunities were extremely limited. Despite its faintness, astronomers continued targeted tracking using the most sensitive instruments available, including large optical telescopes and space-based infrared observatories. Each detection, though marginal, offered valuable data on the long-term evolution of the body, its rotational dynamics, residual activity, and structural integrity after enduring a perihelion passage far closer to the Sun than most interstellar objects survive. Rotational analysis indicated that the tumbling motion had nearly ceased, with a rotation period stabilizing just above 18.5 hours. Minor variations were detected, likely caused by surface irregularities or small asymmetries in mass distribution, rather than ongoing outgassing. The nucleus appeared largely intact, confirming that the internal cohesion of interstellar bodies can withstand both the extreme thermal stresses of close solar encounters and the mechanical stresses accumulated over millions of years of interstellar travel. This observation offered a unique opportunity to study the structural resilience of material formed in planetary systems beyond the solar system. Spectroscopic observations continue to highlight a distinct chemical composition. Carbon-rich compounds remained dominant, with weaker but detectable signals of sulfur and nitrogen-bearing molecules. Water ice was still largely absent, reinforcing the conclusion that the object had originated in a chemically unique environment, likely a cold outer region of a distant planetary system. These findings provided direct evidence of the diversity of small-body chemistry across the galaxy, revealing molecular combinations not typically observed in solar system comets, and offering insight into the processes of planetary formation in other star systems. Infrared measurements indicated that the surface had cooled further but still retained a faint residual thermal signature. This suggested the presence of a carbon-rich insulating crust formed during perihelion, which likely preserved some subsurface volatiles. Low-level, sporadic outgassing may have continued, producing extremely faint dust emissions detectable only by highly sensitive instruments. These measurements confirm that even after extreme solar heating, interstellar bodies could maintain minor activity and preserve internal material. Dust emissions observed in September were sparse and irregular, consisting mainly of silicate and carbonaceous grains consistent with surface material partially eroded during perihelion. Analysis of these particles offered further insights into the mechanical and thermal resilience of interstellar small bodies, showing that the outer layers can survive intense solar heating without catastrophic disintegration of the nucleus. Orbital modelling confirmed the hyperbolic trajectory remained stable, with eccentricity slightly above 1.0003 and outbound velocity exceeding 60 km per second relative to the Sun. Simulations traced its origin to a distant stellar system near the galactic plane, with millions of years spent travelling through interstellar space. Cosmic ray exposure and interactions with interstellar medium likely contributed to the altered surface chemistry, reddened appearance, and carbonized crust, leaving a chemical record of its extensive interstellar journey. The scientific implications remained substantial. The object's survival, chemical complexity, and structural integrity demonstrated that interstellar bodies could endure extreme conditions while preserving both physical cohesion and exotic chemical signatures. This suggested that many similar objects drift through the galaxy, carrying material from a wide range of planetary environments. Observing such bodies provides critical insight into chemical diversity, planetary formation, and the transport of matter between star systems, offering a rare opportunity to study material originating from beyond the solar system. Global interest persisted. Professional and amateur astronomers collaborated to refine positional, rotational, and photometric data, highlighting the importance of coordinated monitoring for transient interstellar phenomena. These efforts ensured that as the object faded further, the scientific record remained as complete as possible. As September concluded, projections indicated that the object would soon fade beyond detection limits. Nevertheless, the extensive observations, from perihelion to the distant outer solar system, provided a nearly complete record of its survival, rotation, chemical composition, and dust activity. The dataset offered an unprecedented benchmark for understanding interstellar objects, informing models of both individual behavior and the broader population of material traversing interstellar space. The passage of this interstellar traveler reinforced the extraordinary scientific value of such encounters. Its durability, chemical complexity, and structural persistence revealed the resilience of bodies traveling between stars. Even as it receded permanently into interstellar space, it left a lasting legacy, expanding understanding of planetary formation, chemical diversity, and the dynamics of matter moving across the galaxy. Each interstellar visitor provides a rare and irreplaceable window into the broader cosmos. By October 2026, the interstellar object had reached the outermost boundaries of the solar system, beyond the orbit of known trans-Neptunian objects, fading rapidly as sunlight became exceedingly weak. Observations were now extremely limited, relying primarily on the largest telescopes and space-based instruments with deep field sensitivity. Despite the challenges, astronomers continued to track its position, rotational state, and residual activity, recognizing that every remaining measurement provided critical insight into the long-term evolution of an interstellar body after surviving extreme solar heating. Rotational analysis indicated that the tumbling motion had essentially ceased, with a rotation period stabilizing around 19 hours. The light curve was relatively uniform, with only minor deviations caused by irregularities in shape or mass distribution, rather than ongoing outgassing. The nucleus remained intact, demonstrating that interstellar objects possess sufficient structural cohesion to survive close solar encounters and the cumulative stresses of interstellar travel spanning millions of years. This finding challenged previous assumptions about the fragility of small bodies travelling between stars and offered a rare opportunity to study the mechanical resilience of material formed in distant planetary systems. Spectroscopic measurements continued to highlight the object's distinctive chemical composition. Carbon-rich compounds dominated, while sulfur and nitrogen-bearing molecules remained detectable. Water ice was still largely absent, reinforcing the conclusion that the body had formed in a chemically unique environment, likely a cold outer region of another planetary system. These chemical fingerprints offered unparalleled insight into the diversity of small body compositions across the galaxy, revealing molecular structures rarely observed in solar system comets and illustrating the range of planetary formation conditions beyond our Sun. Infrared observations indicated that the object's surface had cooled significantly, yet a faint thermal signature persisted. This suggested that the carbon-rich crust formed during perihelion still acted as an insulating layer, preserving some subsurface volatiles. Very low-level sporadic outgassing may have continued, producing faint dust emissions detectable only with the most sensitive instruments. These residual effects demonstrated the object's ability to maintain activity long after the extreme perihelion encounter, offering clues about heat retention and surface evolution under low solar flux conditions. Dust monitoring revealed a sparse and irregular trail of particles. Composed primarily of silicate and carbonaceous grains, the debris appeared consistent with material partially eroded during perihelion. Analysis of these particles provided further insight into surface processes, demonstrating how interstellar small bodies respond to extreme thermal stress without catastrophic fragmentation. The gradual reduction in dust emission over time highlighted the endurance of the nucleus and its capacity to maintain structural integrity in the outer solar system. Orbital modelling confirmed that the hyperbolic trajectory remained consistent, with eccentricity slightly above 1.0003 and outbound velocity exceeding 60 km per second relative to the Sun. Its path reaffirmed an origin from a distant stellar system near the galactic plane, having travelled millions of years through interstellar space. Interactions with cosmic rays and the interstellar medium contributed to the reddened, carbonized surface observed post-perihelion, leaving a chemical record of the object's long interstellar journey. The scientific significance of these observations remained profound. The object's survival, chemical diversity, and structural stability demonstrated that interstellar bodies could endure extreme conditions while preserving both physical cohesion and complex molecules. This implied that countless similar objects may traverse the galaxy, carrying material from diverse planetary environments. Studying such bodies expands understanding of chemical diversity, planetary formation, and interstellar transport of matter, offering a unique window into processes occurring beyond the solar system. Global collaboration between professional and amateur astronomers continued to refine positional, rotational, and photometric data. These coordinated efforts ensured that, even as the object faded toward invisibility, the scientific record remained comprehensive. As October drew to a close, the object was projected to disappear from observational reach permanently. Nevertheless, the extensive data collected, from perihelion through the outer solar system, provided an unprecedented record of survival, rotation, chemical composition, and dust activity. This dataset serves as a benchmark for interpreting future interstellar objects, informing models of their behavior and offering insight into the broader population of interstellar material traversing the galaxy. The passage of this interstellar visitor reinforced the extraordinary value of such encounters. Its resilience, chemical complexity, and enduring structure revealed the remarkable durability of bodies travelling between stars. Even as it receded permanently into interstellar space, the object left a lasting legacy, expanding our understanding of planetary formation, chemical diversity, and the movement of matter across the galaxy. Each interstellar object provides a rare, irreplaceable opportunity to study the wider cosmos and the hidden dynamics shaping it, By November 2026, the interstellar object had travelled far into the uncharted outskirts of the solar system, approaching the threshold where sunlight is barely detectable. Its apparent magnitude had dimmed beyond 25, making routine observations exceedingly difficult. Yet targeted efforts continued using the most powerful ground-based telescopes and sensitive space observatories. Every detection, however faint, contributed critical information about its long-term evolution, rotational behaviour, and structural integrity, offering one of the few opportunities to study an interstellar body after it survived the intense heat and gravitational stress of perihelion. Rotational monitoring indicated that the tumbling motion had fully stabilised, with a rotation period just above 19 hours. Light curve variations were minimal, attributable mainly to minor surface irregularities, rather than ongoing outgassing or internal activity. The nucleus remained intact, demonstrating that interstellar objects possess substantial internal cohesion, sufficient to withstand both extreme solar heating and the mechanical stresses accumulated over millions of years of interstellar travel. Observing such resilience provides unprecedented insight into the structural properties of material formed in distant planetary systems. Spectroscopic studies continue to reveal a distinctive chemical composition dominated by carbon-rich compounds, alongside weaker yet detectable traces of sulfur and nitrogen-bearing molecules. Water remained virtually absent, reinforcing the hypothesis that the object had formed in a chemically distinct environment, likely a cold outer region of another stellar system. The presence of these exotic volatiles and complex compounds offers a rare glimpse into the diversity of small body chemistry across the galaxy and the processes that govern planetary formation in other star systems. Infrared observations showed that the surface had cooled further, though a faint thermal signature persisted. This indicated that the carbon-rich crust formed during perihelion provided continued insulation, preserving subsurface volatiles and allowing extremely low-level activity to continue. Although any outgassing was now sporadic and minimal, the data confirmed that interstellar bodies can retain some internal activity long after exposure to intense solar heating. Dust emission in November was extremely faint, consisting of sparse, irregular particles likely originating from surface microfracturing during perihelion. The composition remained primarily silicate and carbonaceous, consistent with earlier observations, providing additional insight into the erosion processes that act on interstellar objects under extreme thermal stress. The gradual decline in dust activity illustrated the durability of the nucleus and its ability to maintain structural integrity in deep space. Orbital modelling confirmed the hyperbolic trajectory remained stable, with an eccentricity slightly above 1.0003 and an outbound velocity exceeding 60 km per second relative to the Sun. Its trajectory suggested an origin from a distant stellar system near the galactic plane, having travelled millions of years through interstellar space. Exposure to cosmic rays and the interstellar medium likely contributed to the reddened surface and carbonized crust, creating a chemical record of the object's long interstellar journey. The scientific implications of these observations were significant. The object's survival, chemical complexity, and structural stability demonstrated that interstellar bodies can endure extreme conditions while preserving both physical cohesion and molecular diversity. This suggested that many similar objects traverse the galaxy, carrying material from a wide array of planetary environments. Studying such objects provides insight into chemical diversity, planetary formation, and interstellar material transport, offering a unique window into processes occurring far beyond our solar system. Global interest in tracking the object persisted. Professional and amateur astronomers collaborated to refine positional, rotational, and photometric data, ensuring the scientific record remained as complete as possible despite its faintness. This collaboration highlighted the importance of coordinated global monitoring for transient interstellar phenomena. As November concluded, projections indicated that the object would soon fade beyond detection entirely. Nevertheless, the extensive dataset collected, from perihelion to its gradual fade in the outer solar system, provided an unparalleled record of survival, rotational dynamics, chemical composition, and dust activity. This information serves as a benchmark for future interstellar object studies, informing models of individual behavior and the broader population of interstellar material passing through the galaxy. The journey of this interstellar visitor underscored the immense scientific value of such encounters. Its durability, chemical complexity, and enduring structure revealed the extraordinary resilience of bodies travelling between stars. Even as it receded permanently into interstellar space, the object left a lasting legacy, expanding understanding of planetary formation, chemical diversity, and the movement of matter across the galaxy. Each interstellar object offers a rare, irreplaceable opportunity to explore the wider cosmos and the hidden processes shaping it. By December 2026, the interstellar object had receded far beyond the Kuiper Belt, now residing in the remote outer limits of the solar system, where sunlight is nearly imperceptible. Its apparent brightness had dimmed past the capabilities of most ground-based telescopes, and only highly sensitive space-based instruments could still detect its faint presence. Despite the observational challenges, each measurement remained scientifically valuable, offering a rare glimpse into the long-term behaviour of an interstellar body after it survived the extreme heat and mechanical stresses of perihelion. Rotational monitoring indicated that the tumbling motion had fully stabilised, with a rotation period of roughly 19.5 hours. Light curve variations were minimal and attributed to minor surface irregularities rather than ongoing outgassing or internal changes. The nucleus remained intact, demonstrating that interstellar objects possess significant internal cohesion, allowing them to withstand both the intense solar heating of close passage and the cumulative stresses from millions of years of interstellar travel. Such resilience provides invaluable insight into the structural properties of material formed in distant planetary systems. Spectroscopic observations continue to confirm the unusual chemical composition. Carbon-rich compounds dominated the spectrum, accompanied by weaker but detectable traces of sulfur and nitrogen-bearing molecules. Water remained nearly absent, reinforcing the conclusion that the object originated in a chemically distinct environment, likely a cold outer region of another star system. These chemical signatures offer a rare window into the diversity of small body compositions across the galaxy, revealing molecular combinations rarely observed in solar system comets, and illuminating planetary formation processes beyond the Sun. Infrared observations showed that the surface had cooled considerably, though a faint thermal signature persisted. The carbon-rich crust formed during perihelion still acted as an insulating layer, preserving subsurface volatiles. Any remaining outgassing was extremely low and sporadic, detectable only with the most sensitive instruments, demonstrating that interstellar bodies can retain minor internal activity long after extreme perihelion exposure. Dust emission was now nearly imperceptible, with only sparse, irregular particles occasionally observed. Analysis indicated a composition of silicate and carbonaceous grains, consistent with material partially eroded during perihelion. This offered further insight into the mechanical and thermal resilience of interstellar small bodies, illustrating how outer layers can survive extreme heating without catastrophic fragmentation of the nucleus. Orbital modelling confirmed that the hyperbolic trajectory remained unchanged, with an eccentricity slightly above 1.0003 and an outbound velocity exceeding 60 km per second relative to the Sun. Its path reaffirmed an origin from a distant stellar system near the galactic plane, travelling millions of years through interstellar space. Exposure to cosmic rays and the interstellar medium likely contributed to its reddened, carbonized surface, leaving a chemical record of its extended journey. The scientific implications of these observations were substantial. The survival, chemical complexity, and structural integrity of the object demonstrated that interstellar bodies can endure extreme conditions while preserving physical cohesion and exotic molecular compounds. This suggested that many similar bodies drift through the galaxy, carrying material from diverse planetary environments. Studying such objects expands understanding of chemical diversity, planetary formation, and interstellar material transport, providing a rare window into processes beyond the solar system. Professional and amateur astronomers continued to collaborate on positional, rotational, and photometric observations, refining models and ensuring the scientific record remained as complete as possible. This coordination emphasized the necessity of global monitoring for transient interstellar phenomena. As December ended, projections indicated that the object would soon fade entirely from view. Nevertheless, the dataset compiled over nearly a year, from perihelion to deep outer solar system monitoring, offered an unparalleled record of survival, rotation, chemical composition, and dust activity. This information provides a benchmark for future studies of interstellar objects, informing models of their behaviour and the broader population of material traversing interstellar space. The passage of this interstellar visitor highlighted the extraordinary scientific value of such encounters. Its resilience, chemical complexity, and structural persistence revealed the durability of bodies travelling between stars. Even as it receded permanently into interstellar space, it left a lasting legacy, expanding understanding of planetary formation, chemical diversity, and the movement of matter across the galaxy. Every interstellar object represents a rare and irreplaceable opportunity to study the broader cosmos and the hidden dynamics shaping it. By January 2027, the interstellar object had moved well beyond the heliosphere, entering the extremely sparse region of space where the sun's influence is minimal and sunlight is virtually negligible. Observations were now limited to only the largest telescopes equipped with deep field capabilities and sensitive detectors. Despite these limitations, every faint measurement remained invaluable, offering unique insights into the long-term evolution, structural resilience, and chemical preservation of a body that had survived both interstellar travel and an extreme perihelion encounter. Rotational monitoring confirmed that the tumbling motion had fully stabilized, with a rotation period approaching 20 hours. Variations in the light curve were negligible and primarily caused by minor surface irregularities rather than any residual outgassing or structural changes. The nucleus remained intact, illustrating that interstellar objects possess remarkable internal cohesion, sufficient to endure both intense solar heating and the mechanical stresses accumulated over millions of years of interstellar travel. This observation provided a rare window into the mechanical properties of material formed in distant planetary systems and challenged previous assumptions about the fragility of interstellar small bodies. Spectroscopic analysis continued to show a distinctive chemical signature. Carbon-rich compounds dominated with weaker but detectable traces of sulfur and nitrogen-bearing molecules. Water remained nearly absent, reinforcing the conclusion that the object formed in a chemically unique environment, likely a cold outer region of another star system. These chemical fingerprints offered crucial insight into the diversity of small body compositions across the galaxy, revealing molecular structures not typically observed in solar system comets, and providing evidence of the different planetary formation pathways in other stellar systems. Infrared observations indicated that the surface had cooled further, though a faint residual thermal emission persisted. This suggested that the carbon-rich crust, formed during perihelion, continued to act as an insulating layer, preserving subsurface volatiles. Any remaining outgassing was extremely low-level and sporadic, detectable only with the most sensitive instruments. These observations confirm that interstellar bodies can retain some internal activity long after enduring extreme solar heating, providing critical information on heat retention and surface evolution in deep space. Dust emissions were now minimal, consisting of only sparse, irregular particles likely resulting from microfractures in the surface material. The composition remained primarily silicate and carbonaceous, consistent with earlier observations. These measurements offered additional insight into the erosion mechanisms acting on interstellar objects, demonstrating how surface layers respond to extreme thermal stress without catastrophic disruption of the nucleus. Orbital modelling verified that the hyperbolic trajectory remained unchanged, with eccentricity slightly above 1.0003 and outbound velocity exceeding 60 km per second relative to the Sun. The trajectory indicated origin from a distant stellar system near the galactic plane, with millions of years spent traversing interstellar space. Exposure to cosmic rays and interstellar medium had likely contributed to the reddened surface and carbonized crust, leaving a chemical record of the object's long interstellar journey. The scientific significance of these observations remained profound. The survival, chemical complexity, and structural integrity of the object demonstrated that interstellar bodies can endure extreme conditions while maintaining both physical cohesion and exotic chemical signatures. This suggested that numerous similar objects drift through the galaxy, transporting material from diverse planetary environments. Studying these visitors provides insight into chemical diversity, planetary formation, and the transport of interstellar matter, offering a rare glimpse into processes occurring far beyond the solar system. Collaboration between professional and amateur astronomers continued, refining positional, rotational and photometric data. Global coordination ensured that, even as the object faded toward observational limits, the scientific record remained comprehensive. As January concluded, projections indicated that the object would soon become entirely undetectable. Nonetheless, the dataset collected, from perihelion through the outer solar system, provided an unparalleled record of survival, rotation, chemical composition, and dust activity. This information serves as a benchmark for future interstellar object studies, informing models of individual behavior and the broader population of interstellar material moving through the galaxy. The passage of this interstellar traveller reinforced the extraordinary scientific value of such encounters. Its durability, chemical diversity, and structural persistence revealed the resilience of bodies travelling between stars. Even as it receded permanently into interstellar space, it left a lasting legacy, enhancing understanding of planetary formation, chemical diversity, and the dynamics of matter across the galaxy. Every interstellar object represents a rare, irreplaceable opportunity to study the hidden processes shaping the broader cosmos. By February 2027, the interstellar object had advanced far into the depths of the outer solar system, now in a region where sunlight is almost negligible and observational opportunities are exceedingly limited. Only the most sensitive instruments, including deep-field space telescopes and large ground-based optical arrays, could detect its faint signal. Despite these challenges, each remaining measurement was invaluable, offering insight into the long-term structural, rotational, and chemical evolution of an interstellar body that had survived both millions of years in interstellar space and an extreme perihelion encounter. Rotational analysis indicated that the tumbling motion had stabilized completely, with the rotation period nearing 20 hours. The light curve showed minimal variation, largely due to minor irregularities in shape, rather than any residual outgassing or internal changes. The nucleus remained structurally intact, providing clear evidence that interstellar objects can maintain cohesion under both extreme thermal stress and prolonged mechanical forces from interstellar travel. This offered a rare observational benchmark for understanding the mechanical properties of small bodies formed in distant planetary systems. Spectroscopic observations continued to reveal a distinctive chemical profile. Carbon-rich compounds dominated, with weaker yet detectable traces of nitrogen and sulfur-bearing molecules. Water remained virtually absent, supporting the conclusion that the object had formed in a chemically distinct environment, likely a cold outer region of another stellar system. These molecular signatures provide a direct glimpse into the diversity of small body compositions beyond the solar system, highlighting processes of planetary formation and material transport that differ from those observed in our local system. Infrared measurements showed that the surface had cooled further, though a faint residual thermal signature remained detectable. The carbon-rich crust formed during perihelion still provided insulation, preserving subsurface volatiles. Extremely low-level sporadic outgassing may have continued, detectable only by the most sensitive instruments, demonstrating that interstellar bodies can retain minor activity long after close solar encounters. This provides valuable information on thermal conduction, crust formation, and surface evolution in deep space. Dust observations were nearly imperceptible, consisting of sparse, irregular grains primarily composed of silicate and carbonaceous material. These particles likely originated from microfractures in the surface, created during perihelion. Analysis of these grains offered additional insight into the mechanical and thermal resilience of interstellar small bodies, illustrating that their outer layers can survive extreme heating without catastrophic disintegration. Orbital modelling confirmed the hyperbolic trajectory remained unchanged, with eccentricity slightly above 1.0003 and outbound velocity exceeding 60 km per second relative to the Sun. The path indicated origin from a distant stellar system near the galactic plane, with millions of years spent traversing interstellar space. Interactions with cosmic rays and the interstellar medium had likely contributed to the reddened, carbonized surface, leaving a chemical record of its extended journey. The scientific significance of these findings remained substantial. The survival, chemical diversity, and structural stability of the object demonstrated that interstellar bodies can endure extreme conditions while maintaining physical cohesion and complex chemical signatures. This suggests that numerous similar objects may traverse the galaxy, transporting material from diverse planetary environments. Studying these bodies provides crucial insight into chemical diversity, planetary formation, and interstellar material transport, offering a rare opportunity to examine processes occurring far beyond our solar system. Global collaboration between professional and amateur astronomers continued, refining positional, rotational, and photometric data. Coordinated observation efforts ensured that, even as the object approached the limits of detectability, the scientific record remained comprehensive and reliable. As February concluded, projections indicated that the object would soon fade beyond observational reach entirely. Nevertheless, the dataset collected, from perihelion through deep outer solar system monitoring, offered an unprecedented record of survival, rotation, chemical composition, and dust activity. This dataset establishes a benchmark for interpreting future interstellar objects, informing models of both individual behavior and the broader population of material traversing interstellar space. The passage of this interstellar traveler reinforced the extraordinary scientific value of such encounters. Its durability, chemical complexity, and enduring structural integrity revealed the resilience of bodies moving between stars. Even as it receded permanently into interstellar space, the object left a lasting legacy, expanding understanding of planetary formation, chemical diversity, and the dynamics of matter across the galaxy. Every interstellar visitor represents a rare and irreplaceable opportunity to study the hidden processes shaping the wider cosmos.